Welcome to Exam 2 Review. So this is Exam 2 Review. Your exam is tomorrow, 07/07/16. And for those of you that got the proctor sites out to me with email addresses, I have sent that information out and will continue to do so throughout today. So if you have not done that, be sure to do that. Okay, this exam too will be over chapters 4 and 5. So as I look, I'm just going to kind of give you an outline of where I would focus my energy and work problems and be able to do these problems and read the material in your book in these sections that I specify, very detailed like, because I would say a third of the exam will not even be calculations. They will be theoretical questions of some sort. Okay, so let's go. I'm looking in your TRO book, and if you want to get your TRO textbook, I would start reading for sure and understand section 4-2. This is on page 140. And it's talking about reaction stoichiometry. You need to understand how to make conversion factors. So when you do a mole to mole conversion, that's on page 141, you get those numbers that go with the moles of certain substances from your balanced equation. And so if you continue in that section, which is a very important section, you will understand that you have to write a balanced equation, and if you go from grams to mole, then you can go to mole of another substance. So let's say we have a reaction such as 6 CO2 plus 6 water, 6 oxygen plus sugar. This is photosynthesis, isn't it? Okay, so here if we're giving grams of CO2, like 40 grams of CO2, we can convert this into its molar mass. Now when you do molar mass, you're going to look at the periodic table and you're going to calculate how many grams make up CO2. And so that's 16 times 2 plus 12, and that works out to be 32, I think 44 grams per 1 mole. And then once you get there, your mole of CO2, you can convert that to anything. You can go to moles of water, you can go to moles of glucose. So let's say we wanted to go moles of glucose. Well, then your conversion factor would be your coefficients here, and for 6 mole of CO2, you have 1 mole of glucose. And then, of course, depending on the question, if it asks for grams of glucose, then you can use the molar mass and calculate for 1 mole of glucose. You can calculate 6 carbons, 12 hydrogens, or 6 oxygens and figure out the molar mass. And yeah, that's like 180.2 grams per 1 mole. So you need to be able, these are called mass to mass conversions or mole to mole conversions or mass to mole to mass conversions. And that's how you do that. And that's on section 4-2. That's probably worth like, I don't know, 5 or 6 questions. So understand how to do that. A couple of questions are going to come straight from limiting reagents. So you're looking at 4-3, limiting reagents. How do you spot a limiting reagent? Well, you're going to give amounts of both your reagents. So you'll be given either grams or moles of both reactants. And then you have to, if you remember correctly, you have to figure out how many moles of product. So you're going to take grams or moles of each reactant, and you're going to do moles of the same product. And the one with the less number of mole of product That is your limiting reagent. And at that point, you want to work every problem based on that limiting reagent. The other thing you need to know how to do is theoretical yield and percent yield. Theoretical yield is always what you're calculating. So when you do these grams to moles and you figure out how many moles of a product you have, you are calculating theoretical yield. Actual yield, which I just do AY, actual yield would be given to you in the problem. So that would have to be given to you. And then so if you want percent yield, you do actual over theoretical times 100%. And that is on section 4-3. Let's see, what else do we have here? Solution concentration. Yes, you need to be able to do molarity. So 4-4, you need to be able to work problems. Now each one of these that I'm talking about here are calculation problems. So you're going to have to be able to do the calculation. So I would read these sections, but I would really focus on solving problems. So in 4.4, you're dealing with solutions. So you're dealing with molarity, which is a big M. Whenever you see molarity, you want to put that as moles of whatever your compound is over either 1 liter, or you could put that over 1,000 milliliters if your problem is asking about milliliters. And remember, when you get a problem like this, if you're given moles of a substance and you're given a molarity, then you can convert, or grams, you can convert that to moles using molar mass. So you need to work those problems. Your dilution, I would know M1 V1 equals M2 V2. You'll recognize that problem if it's the same substance. So be able to recognize those problems and work those. Section 4-5. Now 4-5, you're dealing with precipitation, you're dealing with electrolytes. I would be able to have some examples of what electrolyte is: a strong electrolyte and a non-electrolyte. So pick out some examples for that, and that's on page 159. So as you can see here, it says sodium chloride, because it breaks up into its cation and anion, would be a strong electrolyte. And in water solution, it would actually turn the light on. Look at figure 411. We are required to put some figures and graphs in every exam. So look at your figures, because they're going to come from the similar pictures in your chapters. As you can see here, we have sugar solution, which is carbon, hydrogen, and oxygen. And it is a non-electrolyte because it doesn't break up. So if you look at figure 412, you see that the sugar sucrose molecule here stays all together and does not break up in plus and minus. Well, what's the difference? Do you remember when we were talking about writing ionic compounds and covalent compounds? And covalent compounds have the nonmetals? Yeah. So your covalent compounds, which are composed of nonmetal elements, like phosphorus trioxide, remember we name them by the prefixes, dinitrogen, trioxide, these are nonmetals with nonmetals. These form covalent compounds. These compounds do not break up in aqueous solutions. They don't break up into charges and plus and minuses, and therefore they're considered a non-electrolyte solution. Okay, look on page 180. It talks about strong acids. Acids break up, HCl breaks up into H plus and Cl minus. A strong acid is a strong electrolyte. We have acetic acid here. Acetic acid has is vinegar, and those are examples, and that would be a weak electrolyte. Okay, this leads us straight into the solubility of ionic compounds. Hopefully you have already memorized table 4-1, and you recognize that if compounds have lithium, sodium, potassium, ammonium, nitrate, or acetate, then they're going to be aqueous. They're going to be soluble. And there are no exceptions to these. And then you can recognize the ones with the exceptions and be able to write the products of the reactions and figure out which one's going to be a precipitate. And that example, you work those problems on 162 and also section 4-6. So as you can see there on page 163, you get an insoluble lead iodide. That is worth 2 or 3 questions, being able to predict products and determine whether something is soluble or aqueous, an electrolyte versus a non-electrolyte. So be able to do that section. Okay. Be able to write a net ionic equation. So section 4-7. Be able to write a net ionic equation. And that talks about spectator ions on page 167 and what a net ionic equation is. So be able to do that. You can read over 4-8 about acid base gas evolution reactions. You do need to know an acid plus a base equals water and salt. You need to be able to write that neutralization reaction because you're going to have those coefficients in order to work a titration problem. And that is what this chapter is about on page 171. So let me just go back and write down so recognize your acids on page 169, but you definitely want to know table 4-1. Be able to do acid-base reactions. Okay, now I would be able to do example 4-14, and that's on page 172. The other problem that I think is worth a couple of questions on the exam is oxidation reduction. If you can do the problems for oxidation reduction reactions that are given to you in your recitation problems, you should be fine. You're going to have to know your rules. Your rules are on page 177 because you will have to assign oxidation states. Basically, you can look at the periodic table, and if you see any of your diatomics in their gas state, that would be a 0 oxidation state. If you see metals in their solid state and their elements, that would be a 0 in their natural state. So when are they not in the natural state? So like if you see calcium solid, well, calcium is a solid at room temperature on the periodic table, so this would have an oxidation number 0. Chlorine, Cl2 gas, well, chlorine is a diatomic gas, and it would have an oxidation of 0. But when these are added together and you make calcium chloride, now in order to make that ionic compound, which you've already done, this is a +2 and chloride is a -1. That is actually it. And there's 2 of them, so yes, it totals to -2, but each chlorine is a -1. So then you can compare them across the reaction arrow here. So here's your reaction arrow. So calcium went from 0 to +2. That's an increase. That would be oxidation. So, chlorine. Sorry, calcium. Calcium went from a 0 to +2. It's oxidized. What happened to chlorine? Chlorine went from 0 to -1. This is reduction. So Cl2 is reduced. Anytime you see fluorine, it's a -1, hydrogen is a +1, oxygen is -2, group 7A is -1. I'm reading you the table on page 177. Okay, be able to do those problems. Work example 4.17, the oxidation states. And that takes you through chapter 4. Now, you got 25 questions, so half of them come from chapter 4, and then half of them come from chapter 5. So let's look at chapter 5. Chapter 5, I told you from the beginning, you need PV equals nRT. You can get pretty much almost everything you need from PV equals nRT. You are given the gas constant, 0.08206 liters atmosphere per mole Kelvin. That tells you that you need temperature in Kelvin. So anytime you get degrees Celsius, you add 273 Kelvin. N would be moles, because you have moles here. Volume would be liters. Pressure needs to be in atmosphere. So that tells you you need to, on page 196, excuse me, page 196, 197, section 5.2, you need to be able to convert millimeters of mercury to atmosphere. You need torr to atmosphere, right? So you have your table 5.1 right there, and you see 1 millimeter mercury equals torr, 760 torr, okay? And also 760 millimeters of mercury equals 1 atmosphere. So you need to be able to go back and forth for that. So that's a conversion you're going to need to know. So know it. The other one, section 5.3. Now, I would also pay attention to graphs that you may see here in this section. This is a great place for graphs and relationships and figures. You won't be asked exactly to know Boyle's law is this, and Charles' law is this, and Avogadro's law, but you better be able to tell by PV equals nRT that that volume is inversely proportional to pressure. I would read these. I would look at the pictures. I would recognize the figure 5.7. I would recognize these pictures. I would recognize these relationships. You got Charles' law where you got Charles' law where you have V is proportional to T. And then you can see you have figures on page 202 for those. And then you got Avogadro's law, which volume is proportional to the number of moles, and you have a figure there that shows you a graph of as the number of moles increase, the volume increases. So that's important. So not only would I recognize those, I would focus on the figures in that and be able to manipulate this equation like I showed you in the recitation. And then that leads you into section 5.4, which is the actual PV equals nRT. And it talks about how you have to have your constants and how you need everything in its certain units. It talks about examples of how to apply it. Yes, you'll have to apply this to a couple of problems. Section 5.5 has some good questions about STP. Well, what's STP? 0 degrees Celsius, but we don't deal with Celsius, right? We're dealing with 273 Kelvin. And we're talking about 1 atmosphere. So whenever it says STP, you have a conversion factor. 1 mole of whatever gas equals 22.4 liters. Now what if you forget that? Well, you can put it in the PV equals nRT for 273 Kelvin and 1 atmosphere and 1 mole for N. And you can solve for volume. Okay? And you would get 22.4 liters. I would know density equals PM over RT. And if you get a question that talks about density and molar mass and you're dealing with those constants, I would pull that equation out. And there's a problem on page 211 that talks about that. Molar mass of a gas. 5.6 talks about partial pressures, I would be able to work a couple problems with that and know that the P total is just a combination of each gas, Dalton's law of partial pressures, and then you have the mole fraction is proportional to the total moles. So if you have a mole of A and over the total moles, and then the pressure of A would be your mole fraction, which is just a fraction, times the pressure of the total. And that is because of this equation here that Dalton found out that they're not interacting. Example 5.6 is good. I would do that. I would focus on 5.7. I'd be able to do some problems in section 5.7 where you do the stoichiometry examples 5.12 and 5.13. Section 5.8 is an excellent area for non-calculation type questions since we are required to give you these. So we're talking about the molecular theory, kinetic molecular theory, and it talks about, I would read these. I would read this with a great detail about the basic assumptions of the kinetic theory on page 223. I would understand that the reason why it works is because you're assuming that the gas molecules are not interacting with each other. So that means they don't have attractions to one another. So I would continue to read this section and understand temperature and molecular velocities on page 226. I would look at the figures on page 227. I would understand that what these figures are telling us is that as our mass is increased, that our velocity decreases because the root mean square velocity on page 227, URMS, is equal to the square root of 3RT over the molecular mass. And see how that relates to the figure on 5.16. So you might have to solve some non-calculation. 5.9 just tells you that the effusion or diffusion, the path that these molecules will take, is proportional to its molar mass. That's its molecular mass. So notice that this is in the bottom. So as the molecular mass increases, your rate is going to decrease, okay, because it's bigger. Bigger things don't travel as fast, right? Now, I know that we worked a problem in section 5.10 for real gases, and we talk about ideal behavior and non-ideal behavior. You will not have to use that equation in the van der Waals equation on page 233. You're not going to have to work that, but I do want you to read section 5.10 and be able to understand when do gases behave under ideal behavior and when do they not. And that would be considered a real gas. And you can see on figure 5.26, you have a figure talking about how gases deviate from ideal gas to real gases. And that should be worth a non-calculation kind of problem. All right, so that's what we have. Like I said, I've got to get your proctor information out. If you have not sent me a contact information, I need that. And if you have any questions, I'll be checking email every few hours and can respond to you. And good luck.